Morning. How are you guys doing today? Ready to rock and roll, right? Why do all stars follow the same pattern? And what I mean by that is that why do 90% of the stars fall along the main sequence? Why is that? So how do stars know that they should be on the main sequence in the first place? Can we come up with some sort of idea about why that is? We have enough tools now that we can discuss this. Okay? And the one thing that I'm going to start off with is this idea. Okay? A higher mass star has a higher core density. In other words, when you have high mass and you collapse down, the core has a higher density. You have packed more objects into the same area or the same volume. Okay? We'll start off with that idea. Now I'm going to lead you through just a series of questions. Okay? Realize you have all of the information to tell me why stars fall on the main sequence. Okay? Here we go. Question 1. Given that a higher mass star has a higher core density, let me ask you this. In which star will the rate of fusion be higher? A low mass, a medium mass, or a high mass star? Take a minute. Go ahead and think about that. Got it? Good. Here's the idea. Let's conceptualize this. Let's say that we're all together again, okay? And we're all sitting in SC-136, and we decide to perform an experiment. Okay? I'm going to blindfold all of you and walk you out into the lobby of the Science Center. So we're all currently blindfolded. We're sitting in the lobby of the Science Center. And now I tell you to walk around. Oh yeah, we can't talk. Don't talk. Okay? So we're blindfolded. We can't talk to each other. Okay? We're just going to walk around. Now imagine that situation. Now the next situation is I'm going to blindfold you. We can't talk. And I'm going to walk you over to the Horner Center and tell you to walk around. In which situation are you more likely to run into somebody? When you're blindfolded walking around randomly in the Science Center, or when you're blindfolded and walking around randomly in the Horner Center? And you would say, the Science Center. And I'd say, why? Why are you more likely to run into each other if you're in the Science Center lobby as versus the Horner Center gym? And you would say, probably something along the lines of the area or the volume that I can walk around in is smaller in the Science Center lobby. Right? I'll say volume right now because really we need volume for a star. Okay? So the idea is this: as I decrease the volume, I am increasing the density. And by increasing the density, how closely packed you are together, I increase the chances of you running into each other. Okay? So if I increase the chances of you running into each other, that's increasing the chances that, no, I'm going to switch gears here, that increases the chances that you will fuse together. If you increase the density, you increase the rate of fusion, which means that high mass stars have the higher density, which means they will also have the higher rate of fusion. Okay. So the next question for you. In which star will the core temperature be higher? Go ahead, think about that for a second. Got it? Good. Now, don't forget, fusion is how a star produces this energy, right? It's converting mass into kinetic energy of the helium atoms. So if the rate of fusion goes up, I am producing more helium atoms, which are running around. And so therefore, I should have a higher temperature. The rate of fusion will dictate the temperature of the core. So a higher rate of fusion will correspond to a higher temperature, core temperature. Okay? So again, we have the high mass star. High mass star, higher core density, higher rate of fusion. Higher rate of fusion, higher core temperature. You follow me so far? Next question for you then. Which star will have a higher layer temperature? So now I've transitioned from the core to the outer layers. Okay? And it doesn't matter if it's a high mass or a medium mass star. Okay? So go ahead, take a minute, think about this. Which star will have a higher outer layer temperature? Okay, good. Well, we run through the whole thing. If the core temperature is higher, and the core is responsible for heating, if you will, the outer layer, then the outer layer temperature should be higher for higher masses. Okay? So higher masses, higher core temperature, that means that the outer layer of the star should be at a higher temperature. Okay, so higher temperature. Next question. Yeah, I just keep walking through. Like I said, you have all of this information now. You just need to realize that you have to put it in order. Okay? Which star will have faster moving gas particles in the outer layer? Ha. You say, now I'm on to you, Greg. Higher temperature means that the gases in the outer layers are moving faster. Higher temperature, higher kinetic energy. Higher kinetic energy means they're moving faster. So it's got to be a high mass star again. I say, you're on the right track. Everything's going well here. Okay? Last piece. Which star will physically be larger? You got it. I'm sure you got it. Higher temperature, higher kinetic energy for the outer layer, which means that the higher kinetic energy, that means that those atoms that are moving faster can move further away from the center of the star. And so a higher mass star will give you a larger radius. So let's walk through again. We said if it has a higher mass, it has a higher core density. Because of that higher core density, the rate of fusion will be higher in the core. Higher rate of fusion, higher core temperature, higher outer layer temperature. Higher outer layer temperature means a larger kinetic energy, and a larger kinetic energy means that those particles can move further from the center. So you have a physically larger star. You've got it. We now have an idea, a model for why the main sequence is being followed. We've got it. We've got everything we need. Last question for you. I should tie this in. I forgot. Which star will have a higher luminosity? It's the double whammy, right? You have not only a higher layer temperature, but you have a physically larger star. It's the double whammy. Of course, the high mass star is going to have a higher luminosity. Okay. Higher luminosity means that it will also lose energy faster. Okay. So apparently I just asked you a series of like 8 or 9 clicker questions where the answer was C, 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 C. You know, like 9 C's in a row. Okay. Go ahead. Take a minute, review that if you need to. Okay. This is really critical. Okay. This is why stars fall on the main sequence. Okay. Okay. So let's start off with this. What if the core of a star is too large, physically in size, in volume? Well, if the core is too voluminous, that means the density in the core is too low. Well, if the density of the core is too low, what happens to the rate of fusion in the core? It's too low. Well, if the rate of fusion in the core is too low, how about the core temperature? Also too low. Well, if the core temperature is too low, what can you tell me about the outer layer temperature? Also too low. Okay. Which means that the particles in the outer layer are moving, I'll put in quotes, too slow. Well, what does this mean about the size of the star, the physical size? If the outer layer isn't moving fast enough, that means that the physical size of the star is decreasing. Okay? In other words, if the core of the star is too large in volume, the outer layers of the star will tend to collapse. Well, if the outer layers of the star tend to collapse, what can you tell me about the core of the star, the volume of the core of the star? It will collapse. What will happen is that the physical size of the star will decrease, the core will decrease in size, and what happens is that the volume, since the volume of the core is decreasing, it will slowly increase the rate of fusion in the star. So a core that's too large will decrease in size in order, the core will decrease in size and slowly increase the rate of fusion, okay, to compensate. So if a core is too big, it will compress. Okay? It's too big to support the size of the star. That means the star will compress and the rate of fusion will go up. Similarly, we can play the same game. If the core is too small, the rate of fusion will be too high in the core, which means the outer layers of the star will be too warm and the entire star will expand. Okay? And that's why we find stars on the main sequence. Okay? If they're too small, they will expand and rise in temperature until they're back on the main sequence. If they're too large, they will compress until they're back on the main sequence. So that's why you can think of the main sequence as kind of being that Goldilocks. Okay? And what happens is that the energy that's produced in the fusion reaction in the core is emitted via the surface. So the size of the star will adjust to make sure that the energy being produced in the core is being emitted through the surface. The technical term, as the title would suggest, is called hydrostatic equilibrium. You don't need to know that. I was just throwing that out there. I think of it as Goldilocks. Okay? Too big, and it will shrink in size until it's just right. Too small, and it will grow until it's just right. This is Goldilocks, is what the main sequence really is. Okay, so I think I'm going to call it quits for right now for this lecture, but go ahead and go back and review. We have the evolutionary tracks of protostars. So how do stars get onto the main sequence? And then the second piece is that why are stars there? Why is it this narrow strip along the HR diagram? It's because of this too big, too small kind of idea. So go back and review that idea, and we'll pick up there next time. Hey, thanks for your attention. I'll see you soon.